Hello everyone and welcome to a new nCine video. Today I would like to show you a new feature coming soon to the engine, custom memory allocators. The way the engine works today is that every memory request goes through the C++ operator new and operator delete. They are based on malloc and free, the usual memory functions of the C language. There is nothing wrong with that and most programs work exactly in this way, but for a game engine some additional flexibility can come a long way. A custom allocator would acquire a big chunk of memory from the system just once, and then serve memory requests by dividing it in smaller pieces. This behavior has performance implications, as it is now no longer dealing constantly with the operating system, and it can make the engine more compatible with esoteric and embedded platforms with unusual memory requirements. Lua, DRM GUI, and Nuclear all support the specification of a custom user allocator, and they can work with the nCine ones without any problem. Let's see how the allocators work with the help of this example application. It was very useful during the development too, to show memory status and debug the code. There are 4 different types of allocators: linear, stack, pool, and free list. They all have a different purpose and they are useful in some specific cases. Even the linear allocator, the one we're going to start with as it is the simplest one, is useful in some cases. As a matter of fact, a kind of linear allocator was already present in the engine, inside the render buffers manager class. This kind of allocator can allocate in constant time, doesn't have any kind of memory overhead beyond the alignment requirements, but it doesn't do any allocation bookkeeping and thus it cannot deallocate any memory. It can clear all the memory at once though, a useful characteristic to implement, for example, a fast per frame scratchpad memory. Let's choose a buffer size. The default 1 KB works just fine, and then create a linear allocator. You can see there is now a new entry in the allocators list, showing the object pointer in memory, its type, its size, how much memory has been used, the number of allocations, the buffer address, and some actions. We can perform different allocations and you will see in the memory map a yellow entry per each one of those. There will also be some gray area corresponding to the memory overhead introduced by the alignment requirements. You can notice that we cannot free or reallocate any allocation, but we can clear the whole list in one go. The stack allocator introduces a header at the start of each allocation to keep track of the address adjustment made to satisfy the alignment requirements. This is evident in the gray area that now precedes every allocation made. This makes it possible to deallocate or reallocate the last allocation made. That's why it's called a stack allocator. It works as a leaf list of allocations. The last one has to be the first one to be freed. It also supports a debug mode where it can keep track of the last allocation made and enforce this behavior with an assert. The pool allocator is a very classic allocator type for game development. It allows very fast allocations and out-of-order deallocations when the allocations have all the same size and alignment requirements. This is why, before creating it, we have to choose those 2 parameters. They will stay the same during the allocator lifetime. You can see that the memory has been divided in a list of 3 blocks. They are tightly packed because the alignment adjustment needs to be done just once. There is no header before an allocation, as they all have the same size and alignment. Updating the free list happens in constant time, whenever we allocate or deallocate. We can enjoy out-of-order deallocations, but we cannot reallocate to a different size, of course. The last allocator type is the most complex one, the free list allocator. It can completely replace malloc, realloc, and free, as it is capable of serving allocations of different sizes and alignments and deallocating out of order. It is also able to potentially reallocate every allocation, if not in place, by copying memory to a new and bigger allocation and deleting the old one. The way it works is by having a linked list of free blocks, in a way similar to the pool allocator. Instead of just having a pointer to the next one, each free block header also stores the size of the block. Before performing an allocation, there are some additional settings that we can change. The first one is the fit strategy. With a best fit strategy, the allocator will scan the whole free list and then choose the smallest block that is big enough to fit the allocation. The worst fit strategy is just the opposite. It will always choose the biggest free block. The first fit one is the fastest, as it will stop as soon as a block big enough is found. It has a downside to potentially create more fragmentation. And with fragmentation, here comes the second option. It is possible to make the allocator scan the free list and attempt to merge together adjacent blocks at each deallocation, or perform it on request. The last option, copy and reallocation, refers to the allocator's ability to grow an allocation by allocating more space in a different place and copying the memory content. If the option is disabled, then it will only be possible to serve reallocations in place. This was all for today. If you liked the video, please subscribe and don't hesitate to write a comment if you have any questions. Thank you and see you soon.